So I will talk about cosmology and thermodynamics, in particular the first and second law of thermodynamics in cosmology. So this is a different topic, and there is an alternative idea of cosmology, how the cosmological equations or how the cosmological interaction can be achieved from thermodynamics. The basic idea is following. In this case, we have two entities actually. One is the apparent horizon, which I'll come to discuss, and inside the horizon there are matter fields. And cosmology can be described by the thermal interaction between this horizon and the matter fields. So this is the basic idea of this thing. Okay. So let's go. And before going to this discussion, as I mentioned, there are two entities. One is horizon, which sets the causal connection between the observable and the unobservable universe. And inside the horizon, there are matter fields. There are normal matter fields, which we can causally connected. And we need the thermodynamics of these two entities. One is the horizon and the other one is the matter fields. And we do know the thermodynamics of matter fields very well from our usual thermodynamics or statistical mechanics, but we have to know what are the thermodynamic rules or what are the entropies from apparent horizon, or more particularly, why do we need to associate some entropic formalism to the horizon. Okay, so first of all, my point is requirements of thermodynamics in cosmology, and then I will go to the laws of thermodynamics and cosmology. But this is the most important part. Why do we need to associate some thermodynamic quantity to the horizon in the context of cosmology? Let's go. Okay, so this is the basic FLW metric answer in cosmology, which we will use for the especially flat FLW metric. And in this case, one can show that this c by ht, where ht is the Hubble parameter and c is the light speed, it is a constant time hypersurface that sets the boundary of causal connection. And this causal connection, why this boundary is a causal connection boundary, it can be visualized by two ways. The most prominent way is following. See, the Hubble law tells us that the physical speed of any space-time point is proportional to the physical distance, that is v equals to d into h. That is the Hubble's law. So if we go further and further, then the space-time speed becomes further and further. And as a point, if we go beyond that distance, then the space-time expansion speed becomes larger than the speed of light. So suppose I am the observer and there is an apparent horizon which is c by h, and if some light ray is coming radially inward, then that light ray has two kinds of speeds. One speed is the Hubble expansion coming from the space-time expansion, and other one is the peculiar speed of the light speed, which is its own speed. So for the radially inward light ray, if it is beyond the apparent horizon, then the Hubble expansion speed is much larger than its radially inward speed. So as a result, the physical speed of the light ray is always outward and it cannot reach to us beyond the apparent horizon. However, if the light ray is inside the apparent horizon, then its Hubble expansion speed is less than the inward speed, and that's why the light ray can reach to us. So it's the causal connection which sets the boundary between the observable and unobservable universe. Okay. And as we can see, here I am taking c equals to 1. As you can see, Hubble parameter is time dependent, and that's why this cosmic horizon, unlike to black hole case, is dynamical in nature. And that is the main quantity, that is the main concept. Why do we need the thermodynamic in cosmology? See, as I mentioned, there are two kinds of speed. One is the Hubble expansion, which is basically d into h, which is coming from the Hubble's law, and the other one is the formation of apparent horizon speed, because it is 1 over h. So if we take a derivative, then it becomes minus h dot by h square. And these two speeds are not equal, as you can see. The Hubble expansion and the apparent horizon formation speed is very different. So what is the consequence of this? Suppose O is a co-moving observer, and at a particular time t, this is our visible universe, and the radius of this visible universe, suppose, is 1 over h, which is the boundary of the causal connection. And the matter fields inside the horizons are there. After some time, that is at time t plus dt, the matter field is expanding, as well as the Hubble horizon is also expanding, but their speeds are not same. Suppose the Hubble horizon speed is less than the matter field's expansion speed. So what will happen? The matter fields from S1 will reach from S1 to S3, but the Hubble horizon formation goes from S1 to S2 because its speed is less than the matter field's expansion speed. So as a result, my new visible universe becomes S2, not S3, but the matter field goes from S1 to S3. So we will lose some particles, some flux of matter fields we are going to lose, because the matter entity within S1 goes from S1 to S3, but my new visible universe goes from S1 to S2. So we are going to lose some flux, sorry, we are going to lose some matter field energy density during time. And we know that any matter field's entropy is, roughly speaking, any matter field's entropy is proportional to the amount of matter particles. If we are going to lose some matter particles with time, that means the matter field's entropy is decreasing for sure. Now, if we assume that the second law of thermodynamics is going to okay in the context of cosmology, but we see that the matter field's entropy is decreasing, that's why we have to manage some other entropy, that's why the whole entropy should increase, right? Because if we consider only matter field's entropy, it is going to decrease because there is a matter flux through the horizon, outside matter flux. So if we want to behave, or if we want to obey the second law of thermodynamics in the context of cosmology, we have to associate some other entropy so that the whole entropy should increase. And that other entropy is nothing but the horizon entropy. So that the matter field's entropy is decreasing, okay, but the horizon entropy is increasing, the total entropy must increase. And that is the requirement of the horizon entropy, because we want to obey the second law of thermodynamics in the context of cosmology as well. If you want to obey that formula in the context of cosmology, then we have to associate some other entropy, that is the horizon entropy. So the cosmic horizon needs to be associated with an entropy if we assume the second law of thermodynamics in the context of cosmology. Okay. And once we associate the entropy to the horizon, it is natural, we can associate also the temperature, and from the analogy of black hole thermodynamics, the temperature is coming from the surface gravity, and in the dynamical context, we know the surface gravity of horizon is coming from the Hayward-Kodama analysis. So it is the surface gravity in the spatial FLW metric, which is the temperature of the horizon. Now, once we associate the entropy with the horizon in the context of cosmology, now the next question is coming from, what should we do with that entropy? See, these are different approach to cosmology. In the usual approach to cosmology, we have a Lagrangian, we have an action, and from the principle of least action, we get the equation of motion. But in the context of thermodynamics, since we have some entropy of the horizon, we should get the cosmological field equations from the thermodynamic laws. So, first of all, we need to know what is the actual form of entropy for any modified theory of gravity. If we give some modified theory of gravity, then what should be the form of horizon entropy such that the thermodynamic laws will give the same equation of motion as of Einstein equation. And the next one is the cosmological evolution reversible or irreversible? That is the second law of thermodynamics. So the first question is associated with the first law of thermodynamics, and the second law is associated with the second law of thermodynamics. To answer the first question, we can divide the gravitational field equation or the gravitational modified theory of gravity by two stages. One, the gravitational theory with 1 thermodynamic degrees of freedom, and the next one is more than 1 thermodynamic degrees of freedom. In this case, the field equations can be written by this way. See, in these two equations, the Hubble parameter is coming with a single derivative. That's why we need one initial condition to solve that equation of motion, and that's why there are single degrees of freedom. This gravitational theory is single degrees of freedom. The example of such gravitational theory is basically Einstein gravity, where the single order Hubble parameter appears, or the f of q gravity, etc. In this case, only one thermodynamic degrees of freedom appears, that is the Hubble parameter itself. Now, with this degrees of freedom, we define such kind of entity ds. I am not calling the S is entropy till now. I am just defining this kind of quantity, ds equals to minus du by temperature plus some work done, which is proportional to dv, which is the volume change of apparent horizon, by temperature T. Now I have to prove that now if we prove that this quantity is totally differentiable, then we can call it as entropy, otherwise no. So since ds is just a single variable function, because there is only one thermodynamic degrees of freedom h, so it is automatically total differentiable as by definition of a single variable function, and that's why this s we can call as entropy, and that's why we can write s equals to s horizon, that means the horizon entropy. And once we know that this quantity is the entropy, then we can link this equation, this differential equation, as the thermodynamic law for the apparent horizon, where the gravitational theory has only one thermodynamic degrees of freedom, which is basically this thermodynamic law. And if we integrate this differential equation, we get this kind of entropy formula. And for the Einstein gravity, where this function is just h squared, we can retrieve the Beck-Einstein-Hawking entropy for even in the context of cosmology. Okay. Now we can go for the more than one thermodynamic degrees of freedom. We can play the same game actually. First of all, I am taking just one simple example, r plus alpha r square, the Stardust gravity. Here see, here the gravitational field equation contains up to third order derivative of Hubble parameter. if we write the differentiable equation. So here the thermodynamic degrees of freedom is not 1 but h, h dot and h double dot, because the equation itself up to third order, that's why there are 3 dimensional degrees of freedom. Again, I am defining such kind of entropy as before, but unfortunately this quantity is no more total differentiable, as we can prove. ds is proportional to 1 over h4 into total differentiable function. Because of this factor, this quantity is no more total differentiable, and 1 over h power 4 is acting as integrating factor. So by multiplying the quantity ds by integrating factor, we can get a total differentiable quantity, and then we can show that this total differentiable quantity can behave as the entropy for modified theories of gravity. And if we again integrate the equation, the differential equation, we can get the proper entropy for the r plus alpha r square gravity, by which we can retrieve the cosmological field equation from the thermodynamic law. So there are 2 stages. One is the gravity with 1 thermodynamic degrees of freedom and more than 1. So the basic rules are simple. If we want to associate some quantity with entropy, then you have to prove 2 things. Number 1, it is total differentiable, and number 2, it is increasing or not. Now come to the second part, reversibility, irreversibility. So there are 3 parts. First of all, I describe why do we need to associate some thermodynamics into the apparent horizon. Then what is the form of entropy, or what is the form of thermodynamic laws for that apparent horizon. And next come the second law of thermodynamics. It is an extra thing over Einstein's equation. In the usual cosmological sense, we have only Einstein field equations, but in the context of cosmological and thermodynamics, we have this extra constraint coming from second law of thermodynamics. That is usual also in classical mechanics and thermodynamics. So basically, the first law of thermodynamics gives rise to Einstein field equation, but the second law of thermodynamics gives rise to new constraint. And as I mentioned earlier, that in the case of second law, we need 2 entities, horizon and matter fields, and the thermal exchange between these 2 entities. So as I'm just taking a simple example of Einstein gravity, where I showed that the horizon entropy is basically the Bekenstein entropy, a by 4g. I'm taking h bar equals to 1, the Planck constant h bar equals to 1. So the entropy of horizon is given by a by 4g. And if we take a derivative of this entropy, we will see that under the condition of null energy condition, this horizon entropy actually increases, as I already mentioned earlier. So horizon entropy is increasing, number 1. Now come to the matter part. Initially I mentioned that there is an outflux of matter fields. So the matter fields entropy should be by this way: increase of internal energy plus work done, plus there should be an energy flux which is coming from the chemical potential. And to calculate this energy flux, which is very crucial, we have to calculate basically this intermediate volume between S2 and S3, because this is the volume which encapsulates all the matter flux actually within time t to t plus dt. So we have calculated this energy flux, and as a result we get this equation 4, which is the matter fields change of entropy. So see, there are 2 things. Number 1, horizon entropy is increasing with time, but matter fields entropy is decreasing with time because there is a minus sign. So and the temperature is Th and Tm, T horizon and T matter. So the exchange of heat must occur from matter fields to apparent horizon, because the matter fields entropy is decreasing. That means it rejects some heat, and the horizon is taking the heat. That's why the entropy is increasing. And there are only 2 possibilities for this case. If the exchange of heat occurs from matter to apparent horizon, then Th must be equal to Tm, that is one possibility, which is the reversible case, and Th must be less than Tm, which is the irreversible case. Tm cannot be less than Th because the heat exchange is going from matter field to apparent horizon. So these 2 possibilities can occur. The first possibility will give rise to reversible case, and the second possibility gives rise to irreversible case. Now check which of the possibility is actually true. So it turns out that the reversible case, that means the first case, only occurs when omega equals to -1/3. That means the transition from deceleration to acceleration. At that transition point, the universe expansion is momentarily reversible. I'm coming why is that case, and all for the other cases where omega is -1/3 to 1/3, except -1/3 value, -1 to +1/3, the universe expansion is irreversible. And why is this case? Because see, at the case of -1/3, these 2 speeds become equal, and that's why there will be no flux outside of the matter fields. Okay, there will be no flux outside of the matter fields, and in that case the heat rejected by the by the matter fields are exactly equal to the heat gained by the horizon. So that's why omega equals to minus 1/3 is reversible, because there will be no outflux. The flux will be zero. This term becomes zero. Energy flux becomes zero for omega equals to minus 1/3. And for all the other omega, that means during inflation or during radiation or during the present epoch where omega is not equals to minus 1/3, the universe expansion is irreversible. That is the second law. So as I mentioned, there are three parts. First of all, I described why do we need to associate some thermodynamics to horizon, and then I described if we associate some thermodynamics to horizon, then we have to formulate the laws of thermodynamics, because we don't know what are the laws. We do know the laws of matter fields, but we don't know the laws of thermodynamics of the horizon. That's why we have to formulate the laws of thermodynamics for the horizon, and then we come back to how the exchange occurs between the matter field and horizon, so that the cosmological evolution can be nicely described. And this is the exchange. For the transition between deceleration and acceleration, whether it is inflation to reheating or whether it is radiation to dark energy, that momentarily evolution is reversible. Otherwise, all the epochs are irreversible expansion. And that is the take-home message. Determination of the entropy of apparent horizon that is consistent to the FRW equations for a general modified theory of gravity. So I have described what should be the form of entropy for any modified theory of gravity, so that the proper thermodynamic law can be used to describe the Einstein's field equation, rather than coming from an action principle. See, there are no action, there are only entropy and there is only thermodynamic laws. Okay. And then I discussed the first and second law, as I mentioned. Okay.